All right, we just discussed a one-dimensional model of a one-dimensional collision. That is two billiard balls hitting each other and going off in one line. But if you've ever played pool, you know that the balls don't always go off in the same direction. If you look at it from above, you have the cue ball going off and it hits another ball, and then after the collision this ball might go this way and the cue ball might end up going that way. And so you've got a collision that involves momenta, V1 final, or velocities, V1 final and V2 final, that are in two dimensions, and so you have to consider an x and a y dimension, or an x and a y direction. This complicates things, but you can always work them out. I'm not going to show you how to work out every possible problem you can have, but the important thing to remember is that momentum is conserved and there's a possibility that energy is conserved. If I have billiard balls, in physics a billiard ball is code for an energy collision that's elastic. There's no energy lost in the system. I can write down three things about this collision that can help me solve it. I can write down that the momentum of the system is equal to a constant. And I can write down that the kinetic energy of the system is equal to a constant. That is, the kinetic energy afterwards is the same as the kinetic energy before. Well, wait, I said I told you three things. There are actually two things in this. This means that the x component of the momentum is equal to a constant. It doesn't change. And also the y component of the momentum is equal to a constant. So 1, 2, 3 things that control how you describe the system. So how would I apply that in practice? Let's see if I can write those three quantities down in some more detail. So I'm going to explicitly put my frame of reference. There's the x direction and the y direction. And so I have this ball that comes in with some initial velocity, v1 initial. The other ball was sitting there with zero velocity. Okay, so the initial momentum in the x direction, the horizontal component of the momentum in the x direction before, is equal to m1 times v1I plus m2 times its velocity is 0. Okay? And the initial momentum in the y direction, the y component of the momentum in the y direction, well, this ball was only going in that direction, this ball is not moving, so the momentum in the y direction before the collision is 0. There's no momentum in the y direction. Now, after the collision, I've got one velocity, one ball is going off at a velocity v1 final, and I'll call that angle theta. And I've got another ball going off velocity v2 final, and I'll call that angle phi. Okay. Each of those have components in the x and y direction. So let's take the x direction first. After the collision, m1 is going down like this. So the component in the x direction is going to be m1 times v1 final times the cosine of theta. There's the angle, there's the adjacent side, so the x component is going to be cosine of this angle. And similarly for the other mass, the x component of its momentum is going to be m2 times v2 final times the cosine of phi. Okay. And we can do the same thing with the components in the vertical direction, in the y direction. After the collision, we've got m1 going off at a velocity v1 final, and the component in the y direction is going to be equal to the sine of theta, and the other one is going to be m2 times v2 final times the sine of phi. I always like to keep my velocities as constant numbers, so I'm going to put a minus sign in front of here to emphasize that this is going in the opposite direction from that one. That should all come out in the wash. Do I have enough information to solve this problem now? Let's see. I've got, I want to figure out what V1 final and V2 final are and what these two angles are. So I've got 1, 2, 3, 4 unknowns. I've only got 2 equations so far. I need some more physics to apply to this. Well, the other physics that I could apply is if it's a elastic collision, I can say that the initial energy, the initial translational kinetic energy, K initial is equal to K final, and so I can write that 1/2 times m sub I v sub I squared, the initial velocity of this particle, this had no translational kinetic energy, is equal to 1/2 m1 times v1 final squared plus 1/2 m2 times v2 final squared. Okay? So now I've got 3 equations. They're independent equations, I hope. But I said I need 4 equations because I have to find out the 2 final velocities and the 2 angles. All right. Well, in practice, when you do a problem like this, you have to know one of the angles or one of the other velocities. For instance, if you do nuclear physics, if you're one of the people privileged enough to do this, you do this experiment all the time. You take an atom, you throw a neutron in it, you watch the atom or the nucleus of the atom recoil one way and the neutron recoil the other way, and you measure the velocity and angle of that neutron, and that tells you what happened to the nucleus of the atom, what angle it went off in and what velocity it went in. Okay? So this is a completely elastic collision, and I can describe it in 2 dimensions using just the momentum and kinetic energy equations that I used before. All right?